Welcome to Next in our series of videos that are looking at the impact AI is having on a number of key industries. This time we'll explore some current use cases looking at how AI is being developed and deployed in order to advance and revolutionise approaches to space research. Before I get into it though, don't forget to like and subscribe to ensure that you don't miss out on future videos in this series and others covering all aspects of AI. Now, space research covers a wide array of topics, including the effects of climate change, predicting weather patterns, improving disaster response, identifying meteorites, and astronaut health. A notable organisation working to advance our understanding in these areas is the Frontier Development Lab, or FDL. It's a public-private partnership with the European Space Agency and the North American Space Agency, NASA, in the USA. FDL works with commercial partners to apply AI technologies to space science, to push the frontiers of research and develop new tools to help solve some of the biggest challenges that humanity faces. FDL Europe is a yearly research sprint hosted by the University of Oxford that takes place over a period of 8 weeks in order to promote rapid learning and research outcomes in a collaborative atmosphere. The interdisciplinary teams address tightly defined problems, and the format encourages rapid iteration and prototyping to create meaningful outputs to the space programme and humanity. In this video, we're going to look at a number of examples of FDL Europe research. So let's start by looking at a study to better understanding hydrological models. Floods can have a devastating effect on human lives, nature and economies. Between 1995 and 2015, over 2.6 billion people were affected by floods, 56% of these being affected by weather-related disasters. As flood phenomena becomes increasingly frequent and severe, better preparedness and mitigation strategies become necessary. According to the United Nations, having reliable 72 hours ahead predictions of river floods is vital, as they allow emergency agencies sufficient time to prepare, plan their mitigation strategies and deploy response teams on site. Such river flood prediction models already exist, using satellite-derived data, and perform relatively well in most high-income countries. However, these models are lacking in low-income countries due to limited data availability, where there's often the greatest flooding risk. Here's Omar Nivron from the University of Cambridge to tell us more about this research.
So let's start with some footage. You could see here a river flood in Kohistan, Pakistan, approximately 2 weeks ago. This is a devastating river flood, and our project is aimed to help emergency agencies prepare better for such floods like you have seen here. This specific flood has left hundreds of people homeless, without access to food and without clean water to drink. And you might want to calm yourself down and say, this would not happen to me, to you, to us, but this is happening all over the world. So in this video, you could see the red spots over the world map. These red spots coming up on your screen are river floods happening everywhere. And these are becoming more intense and more frequent in many areas of the world due to climate change. And for this reason, it is time for us to act now. So why now? Well, there is the urgency, as I just mentioned, from the exacerbation of severity of events due to climate change. But there's also a new opportunity now. The opportunity is a newly published dataset, a global dataset for river floods. It's called Caravans. This is not our dataset, but this allows us and other teams around the world to access and do analysis and modeling to help better handle flood predictions. This Caravan dataset includes meteorological forcings, for example, precipitation, temperature, catchment attributes, for example, elevation, slope, climatic indices, for example, which climate zone does the river is situated in, and hydrological signatures such as basin areas. So the urgency, together with the opportunity, brings us to a point where we can start actually produce things to help emergency agencies prepare better.
Using the Floodcast AI pipeline, the Hydrological Models FDL team was able to predict with good accuracy the flood risk up to 3 days ahead of time, including with unseen basins and climate zones where the models also performed well. Using these predictions, interactive 3D models could be generated using NVIDIA Omniverse to better visualise the flood risk and aftermaths. Next, let's look at a study based around aerosols in the atmosphere produced by wildfires. More than 17 million people have been affected through major wildfire events over the last 30 years. In addition, the degradation of air quality due to the creation of aerosols and ozone from fires resulted in between 260,000 and 600,000 premature deaths each year. The risk that wildfires pose to people and the environment is increasing due to climate change, and it's estimated that 4% of global vegetation is destroyed by wildfires every year. Pyrocumulonimbus, or Pyro-CBs, are storm clouds produced by particularly large and intense wildfires. These storm clouds create their own weather fronts, which can make wildfire behaviour unpredictable through strong winds and ignite new fires through lightning. Pyro-CBs also convect wildfire aerosols into the stratosphere, where they remain for several months. These events, which can be on the scale of a volcanic eruption, have important impacts on the Earth's climate. The Pyrocast database now provides the most comprehensive Pyro-CB dates, with labelled geostationary satellite images and associated data for 111 individual wildfire events. And the forecasting model has demonstrated an ability to predict behaviour over a 6-hour horizon. Now let's turn our attention and look at an attempt to create a digital twin of Earth. The Digital Twin Earth, or DTE project, set out to discover whether machine learning can learn forecast precipitation by fusing simulated satellite weather data with physical model data to offer a low-cost alternative to expensive simulation infrastructure. Weather forecasting systems haven't fundamentally changed for over 50 years, and they're based on the fluid dynamical flow of the atmosphere, using as much physics-based and observational data as they can computationally afford, such as temperature, velocity and pressure. Given the amount of data like this that exists today, there's an opportunity to produce new neural network models that can learn the attributes of physics from this numerical data and predict the weather with less compute required.
Now, what is a digital twin, and why do we need one for Earth? Well, a digital twin is really just an interactive model that allows us to study counterfactual pasts, presents, and futures of our planet in silico. And as you're all aware, our Earth system is extremely complicated, and so trying to simulate it in full is somewhat of a moonshot. So for this project, we decided to focus on just one subtask: forecasting the global weather 5 days in advance. So why did we decide to focus on this particular challenge? Well, meet Rosie. Imagine she's a farmer in Uganda, somewhere, and Rosie wants to wait for as long as possible before harvesting her crops in order to maximize the quality of her produce. Assume there's a hailstorm coming in, and Rosie only gets to know about it a day in advance. So in that case, probably up to a quarter of her harvest is going to be lost. But if she had 5 days notice, she could probably save most of it by going out and harvest.
So how do these three main data components come together for precipitation forecasting? I will now walk through 3 steps that we used in our framework. Firstly, we start from satellite imagery to go to prediction and estimation of the atmospheric state in a data assimilation step. Next, we focus on the atmospheric state space, and we want to be able to forecast what the future state would look like. As a third step, we focus on the future atmospheric state, and we want to be able to reconstruct what the global precipitation map looks like in a post-processing step. So together, these 3 steps come together and when performed in sequence, form the crust of our digital twin Earth model. So here we can go from satellite observations through atmospheric states to a future precipitation state.
And here's a summary of our contributions. So before the past 2 months, there were no publicly available results on estimating some important state variables from simulated satellite data. Now we've got that. Secondly, we improved some of the publicly available benchmarks to do with state forecasting over a 3-day period, including results on temperature, and we added some new results on some of the so-called wet variables that are particularly strongly correlated with precipitation. And lastly, we also include a novel method of estimating precipitation from Earth observation data using neural networks. However, our contributions don't stop there. We are also going to open source a framework called Pyrain, which we hope will enable future researchers in this domain to accelerate progress towards our vision of creating a true digital twin of our Earth.
So the Digital Twin Earth project team was able to introduce Pyrain, a library to process the 3 data sets efficiently, reducing time and hardware costs and lowering the barrier to entry in this field. So there you go. We hope you found this video interesting in understanding how AI is being developed and deployed to promote space research and advancements and improve outcome for humanity. This video is intended as a summary of the projects mentioned only, so we've put links to the more in-depth case studies in the description below. Do let us know your thoughts on this video and the case studies in the comments below. Also, don't forget to like and subscribe so you don't miss our next video looking at how AI is being employed in another industry sector.